Okay, well, looks like coming on time is not the cool thing I do this week. We'll see if we'll probably have a lot of students come in a little later. Two items of business before we start. We have a peer mentor. We have Oscar right here. So Oscar is a peer mentor. What that means is he works for you. So he's not a teaching assistant. Teaching assistant would work for me. So peer mentor is there for your assistance, and he will be around coming to class and will also help out with the chem quizzes, and we'll sort things out outside class. See if he can help form study groups if you guys want study groups. So that doesn't mean you have to go to study groups. You have to form them. So other item of business, would you guys like it if I created, I can use something called Zoom so that I can cast what's on my laptop out into cyberspace. Like, did you want to be able to bring your own device, like your laptop, and then this screen will also be on your screen? Was that something that you would like to do? Raise your hand if that's a yes. Okay, so okay, well, you can try it out and see if that's also, if people don't want to come to class, they can just chime in that way, like a virtual meeting. But I also have the lectures online too, so after the fact, and also the online lectures. So let's see. So, anyways, all right. Well, let's go into the content then. So we're in chapter 4. Chapter 4 is stoichiometry, limiting reagent, and aqueous reactions. So aqueous meaning water. We talked about solutions. Solutions means homogeneous mixtures, and then we talked a little bit about concentration. So what was concentration? Concentration is amount per volume. So we left off here with solubility rules, and here are solubility rules. And they like these questions on things like the MCAT and PCAT because it's logic. So is the AC not working? Is that you're hot?
I want
Okay.
to.
These are all logic-based questions. So if you can see, here are the solubility rules. The top part is the following things tend to be soluble. So what tends to be soluble? Alkali metals and ammonium. So on the positive side, negative side, nitrates and acetates. And there are no exceptions for those. Also tend to be soluble the halides, well, chloride, bromide, iodide. The exceptions are silver, mercury, and lead. So that means that, generally speaking, the halides are soluble with then those notable exceptions. Sulfates tend to be soluble with the exception of the alkaline earths, strontium, barium, and then lead plus 2, silver, and, well, and calcium is slightly, or calcium. Oh, really? They didn't put that up with the alkalis. It's not even alphabetical order. Huh. Oh well. So alkaline earths, lead, and silver, sulfates tend to be insoluble. And then these things tend to be insoluble. So what is soluble? Soluble means dissolves in water. So sodium chloride salt. Sodium chloride salt is very soluble in water. If you ever made brine before, like for something, if you want to soak brine, it's 3 to 1, so 3 parts water to 1 part salt. So it's at least at room temperature, salt is 25%, so 25 grams per 75 grams of water. It's really soluble. You have to put tons and tons of salt in something before it won't dissolve anymore. So salt, sodium chloride, very soluble, dissolves in water. So calcium carbonate, limestone, doesn't dissolve in water. You learn that in your lab. You throw a piece of, oh, you probably know that from coral. Piece of coral, piece of limestone, piece of marble, you throw it in water, it doesn't dissolve. It's insoluble. So that's what I mean by insoluble. So hydroxides and sulfides tend to be insoluble, with the exception of alkalis and ammoniums, because alkalis and ammoniums are always soluble. Sulfide is insoluble with alkaline earths. I'm sorry, it's soluble. I'm sorry. Sulfide is soluble with alkaline earths, and hydroxide ion is soluble with the alkaline earths. And I can tell you, I personally disagree with that. So calcium hydroxide is that's slightly soluble, I guess so. You can take lime water, calcium hydroxide, also known as lime water. You can drink it and it doesn't bother you. You can actually use it to calm your stomach. Oh, and we have a guest here. Sorry to put you on the spot. You come in. This is Professor Emsley. She's here to observe me. And if you have any questions about agriculture, she is the maven on this campus for agriculture. And then carbonates and phosphates tend to be insoluble, except for the alkalis and ammonium ions. So, and I mentioned this last class, but something to notice, it's the tiny ions. The tiny ions in charge. So the small charged ions and also the big ions. Big ions with small charges, those are the ones that are soluble. Why? Because they're not very strong and they can have an attraction to water. Okay, so let's use this chart to do some things. Predict if this compound is soluble or insoluble. So lead chloride, first one here, lead chloride, and give it that pink dot there. So lead chloride, so we go up to the chart. So chlorides tend to be soluble with the exception of lead. So since lead is a exception, this is no. I'm saying no, or I can say insoluble. So lead chloride is insoluble. Copper chloride. So next one, copper chloride. Chloride is here. It's a halogen. Chlorides tend to be soluble except for silver, mercury, or lead. Copper is not an exception. Therefore, copper chloride is soluble. Okay, calcium nitrate. So nitrates up here. All nitrates are soluble, no exceptions. So no exceptions, that is in fact soluble. Then barium sulfate. Sulfates tend to be soluble, but barium is an exception. So then barium is not soluble. Well, I should say, I'm saying no. Yes is soluble, no is insoluble. So barium sulfate is insoluble. Has anyone ever had a CT scan done of their GI tract? I have. If you drink barium sulfate, stuff tastes terrible, by the way. They even try to flavor, it still tastes bad. But, okay. So does anybody have any questions here, how you follow the logic? Okay. And we talk about a certain type of aqueous reaction. It's called a precipitation reaction. So that's when you take two liquids and you pour them together, and then you have two compounds that are soluble, and when you pour them together, an insoluble compound forms. There's going to be a lab on this. Okay, so not next week, I think the week after. I don't remember the schedule off the top of my head, but we're going to do precipitation reactions in lab. So we're going to form precipitates, and that's a solid. So like, remember when I talked about the name of the elements? We had the alkaline earths, so the alkali metals. Alkali means basic, means not acid. Then there's alkaline earths. Alkaline earths, they're called earths because they tend to form precipitates. You take solutions of them, and what happens? Well, you have the old Greek element. You have the water element, you pour it together, and it forms earth. It forms dirt, the precipitate, so that's why they call them alkaline earths. Okay. And now we're going to use the chart to predict if there's going to be precipitation reactions. And I was reading through my student evaluations, and one of the comments says that I should preface these types of examples by saying, excuse my heteronormality. I'm trying to use this, I'm not trying to offend anyone, I'm just trying to illustrate a point here. So here, we have this example, we have potassium carbonate reacting with nickel chloride. So, and I'm just including these to try and show you that the way that the elements pair up, the positives will always pair up with the negatives. So the positives and positives will not pair up because of the Coulomb book repulsion. So positive and positive don't pair up because they will repel. Negatives and negatives will not pair up because they repel. So only the positive and negatives will pair up. And this is also sometimes referred to as a partner exchange reaction, as shown kind of by the picture. So see here, so like I'm denoting the male kind of as a positive ion and the negative anion as a female. So here, potassium, you have to ask yourself, so potassium, the positive ion, is then going to pair up with the negative anion, the chloride. So in this case, we have the positive ion here, negative ion here. So the red potassium and the blue chlorine. And then you have the nickel. The nickel is going to pair up with the carbonate. So you say, is one of these soluble or insoluble? So we would then write out, so we have potassium chloride plus nickel carbonate. And I know it's not balanced, so let's go ahead and balance the equation. Actually, a little more space. And so 2 potassiums on the left, 2 potassiums on the right by putting the 2 there. Then the chlorides, well then let's look at the carbonates. 1 carbonate on the left, 1 carbon on the right. Then the nickel chlorides, 1 nickel on the left, 1 on the right. 2 chlorines on the left, and then by putting the 2 in front of the KCl, we have 2 chlorines. So that's balanced now. Now we have to go to the chart. So we have KCl and nickel carbonate. So let me go back up to the chart. So the question is KCl or nickel carbonate, is it soluble or insoluble? Okay, so start with the halide. All chlorides tend to be soluble with these exceptions. It's not an exception, so potassium chloride is soluble. Then carbonates down here tends to be insoluble with the exceptions of alkalis and ammoniums. Nickel is not an exception, therefore it is insoluble. Is everyone following my logic there? Anybody have any questions so far? Okay. So now we do in fact have a precipitate here. And I guess I should, the whole equation then would be 2KCl aqueous. This AQ in parentheses, that means it's dissolved in water. Then this plus NiCO3, and then we say a solid. So that's saying that we have a potassium chloride still dissolved in water, and then the nickel carbonate solid. That means a precipitate. Back in the olden days, you would have an arrow going down. So some countries still teach it as an arrow going down. Likewise, for a gas evolution reaction, there's an arrow pointing up. That's the old way of doing chemistry. So if you see an arrow down or an arrow up in probably an older paper or text, that down means precipitate, means solid, up means gas. The way we do it now is we put S for solid and G for gas. Okay, and the next one, we have sodium nitrate and lithium sulfate. So from this, we're going to form lithium nitrate, 2 of them, plus Na2SO4, like that. So we look at lithium nitrate and sodium sulfate. So lithium nitrate, sodium sulfate. So what's nice about this, lithium and sodium are always soluble with no exceptions. Therefore, if you were to mix these two, these are both soluble. This is no reaction. And this RXN, that's chemistry shorthand for reaction. So mixing sodium nitrate and lithium sulfate together will do absolutely nothing. You just now have a bigger mess of water with more ions in it. So, whereas the one on the left here, potassium carbonate and nickel chloride, this will in fact form a precipitate. So, questions? All right, let's see if you follow. Copper chloride and lead nitrate. What is made? Let me get you the chart too. I should have put that on there. Doesn't show. CuCl2 PV. Is that what I had? So copper chloride and lead nitrate. So how many people think A, we're forming copper 2 nitrate solid? How many think B, we're forming lead 2 chloride solid? How many think C, we're forming dichloride nitrate solid? How many think the last one, we have no reaction? Okay, is anyone stuck? Okay, well we had some people going for B. I'm going to go around. So we have back up there. Okay. All right, so I'm going to go around.
See, I'm looking at this backwards. I can't tell which one it is. Like, see what I mean? Like, also, just for the rest of it. I was in the hospital. He has it. Oh, no, he has just that part. Okay, well, that's fine. It's up there. But this was the one I grabbed.
So it's a
One's inside and one's out. So it would be. Go ahead. This is the solid. This is solid. This is inside.
Good, yeah.
Because that's the basic solid. Okay, so yeah, because it's not this. That's the okay. Yeah, that's the gas. And the CL that would mean that would be.
I just do
it's typically soluble, but
I just do the formula.
Right. Right. And so this
So
is
I already
this
just all the formula, everything. When
yeah,
doesn't
this
report,
was
like
inside.
having to solve this
That's
thing,
solid.
just check where it
Right.
is.
You see what I'm saying? Like,
So I
like since
use
this is
maybe
inside part, that's what
right.
it is. And then this.
it's more not.
If I don't know,
It's
I still
soluble,
I
it's just
take one
when
step.
they're bound together that way.
Right.
So when chlorine is
I want
bonded
to
to
okay.
lead to,
Yeah, once you get it,
you have the insoluble.
see it again.
Yeah.
Okay.
So
So then that is.
they get it.
Yeah.
Okay. And that's because I was looking at this, and that would be if it was
They
reversed
give you
essentially.
another,
Yeah.
but with something different.
What it is.
So it's always
Because I was looking at this one. I got it.
And I felt like I was ready, and I felt like I answered it.
Is the actual
No
or is
answer
the actual
was the same
Or the
number.
lid, the lid part is kind of the same bottom, but
That's the solid.
the copper nitrate, because the nitrate's always going to be soluble, so it's always
Sometimes
going to
the answer is like positive, but you said
Yeah.
really negative. So this one I get confused like when I have to do like
I'm hoping he's gonna like everyone. And he's gonna say top 3 exams or review.
Yeah, that's what I was wondering. Right, that's what's
So the lead. So does the lead forms with the chloride?
Yes.
And forms the solids.
Yes.
Right.
Oh yeah.
I mean, I want to say to some wrong. I guess it's like
I like that.
like you were in high school. I didn't see a patient in high school. I remember that I saw that.
I don't. It's just like totally new to me. It's like I've never seen it before. It's good. Yeah, right. Yeah, so cute.
And then calculation.
Trick.
Pre-calculation.
You're skipping trick?
Yeah.
I don't think you can. Oh, you might be able to, but it's supposed to be algebra, pre-calc, trade, calculus.
I don't know. We'll see, but I know I have to take pre-calculation. I think I guess it's. I don't know.
But not calculus.
I cannot remember.
Usually for like a degree, science degrees, calculus, like all the NOAA, every everything from business to science, all needs calculus. Biology needs 3 calculus. Oh, yeah, so this works with chloride.
Pretty much how the answer
It's pretty big. And then trade. What chip are you going for? No, I'm doing
We just did the baby math. And I have on algebra yet. I think I'll be better with the real algebra. It's not. It's more like.
you need another formula for that. I mean, formulas you could just write it down.
All right, so going around, people have converged upon B, and that is the right answer. Another question was, which one do I know is positive and which one's negative? The positive ions are first. So for copper chloride and lead nitrate, which one's positive, which one's negative? The positive ions are first, the negative anions are second. Does anybody have any other questions? Yeah.
When the copper and chloride dissociate, are they free ions in the solution, or do they recombine? Because
So in solution, it's very dynamic,
Yeah.
and dynamic means it's not just static. It's not just sitting there. It's moving around. And the reason why copper and chlorine dissolve is because the water, we haven't learned this yet, but water is polar. That means there's a positive, negative end to it. And typically, so the copper, it's going to have the end of the water is going to kind of go like this around it. So the oxygen end is going to form an octahedral complex. And the idea is that these 6 bonds and then the 2 chlorines, so there's going to be actually 18 bonds from water versus the 3 ionic bonds, the copper plus 2 and then the 2 Cl minuses. The idea of these 18 bonds are, even though they're weaker, they're greater than the 3. And so this complex moves around in water, but then sometimes the waters pop off and a new one comes in or goes around. Also, sometimes the copper and the nitrate, they get close together, and they, instead of like 2 ions, they form 1, Now this copper plus 1 nitrate kind of acts like a +1 ion instead of a +2 ion or a +2 and a -1 ion. So there's a lot of stuff going on in solution. That's something called the Van Hoff effect, and you can learn about that in other classes.
Okay.
So it's not just sitting there, there's all sorts of things moving around. Also, copper is a special compound, a special element. Instead of a perfect octahedron, it actually extends along the z-axis. That's called the Jahn-Teller effect. So these waters are going to be closer than these. I even drew it that way because they're further away. So, okay. Other questions? Yeah. Does that answer your question?
Yeah, definitely.
Okay. Now we're going to talk about the different types of equations. And this is, I know we changed topics quite a bit, but there are different ways to write out equations. So right now, we've already talked about this. Lead nitrate and potassium chloride forms a lead chloride precipitate, and then potassium nitrate in an aqueous solution. This is known as a molecular equation. So you can see that this is, everything's paired up, and it's paired up together with its positive ion with its negative anion. Now, what does this actually mean? So lead nitrate means there's a lead +2 ion, and then there's 2 NO3 anions. So we can write that like this. So we can split that apart. Similarly, the potassium chloride, we can split it apart. And with the lead chloride, that's still a solid, that sits together. But potassium nitrate is soluble, so it's actually in solution here. So this bottom one here is known as the complete ionic equation. So the top one, we pair them up like in molecules. And looking at the top equation, I see lead nitrate. I kind of picture in my mind, I imagine myself going to the stock room, picking up the plastic bottle full of lead nitrate, taking off the top, taking a scoop, and putting that into a beaker, putting water in the beaker, and a second beaker of potassium chloride, scooping that into a beaker. Now I have 2 beakers of that stuff, and I pour it together. So that's kind of like, we have the molecules, and that's the original identities of this. The complete ionic equation down there just says, all right, this solution that I throw in there has all these ions. So I just have this solution, and I've just thrown all this stuff in there, and I mix it together. And then it forms a precipitate, a lead chloride precipitate. Then if you notice something here, these ions here, the nitrate and the potassium ions, they're on both sides of the equation. So kind of like when if you're doing algebra, if you have 2 things on the same side of the equation, you can get rid of them like that. You can similarly, they're still here, but if you akin a chemical reaction, a chemical equation to a math equation, you could get rid of these ions that way. And this is then known as a complete ionic equation. So getting rid of those ions, you can get the simplified complete ionic equation. And also these ions that I put X's on them, they're known as spectator ions. So like if you ever played a sport and you're watching, say you go to a baseball game and you're in the stands. You're a spectator. Are you actively engaged? Are you up to bat? Are you throwing the baseball? Are you hitting the baseball? Are you catching the baseball? No. You're a spectator. You're just observing. So then these ions, in this case, the nitrate and the potassium, they are spectator ions. They are just there. They're not doing anything, but they're there. So, of course, in a chemical equation, they're still there. And now we have a beaker that has potassium and nitrate in it, so it's not like it's not there. But then this complete ionic equation, this is kind of like the Cliff's Notes. I guess we have Spark Notes now. Do you guys, at my age, do you have Cliff's Notes still? Right? When you instead of reading the book, like if you wanna go and read Grapes of Wrath, you could get the Cliff's Notes, and they're like, okay, the Jodes leave Oklahoma, go to California, and it ends with a curious smile, kind of thing. You know, that's the Cliff Notes. That's Grapes of Wrath, right? So this is the Cliff's Notes of chemistry. It's just, I want to know what happened. Well, in this equation, lead and chloride met and they precipitated. That's all I care about, is what happened. I don't care about these spectator ions. I don't care about the Jodes meeting the preacher. We can forget that, right? So that's the Cliff Notes. Okay. And I'm sorry, we changed topics quite a bit in the beginning. The next type of aqueous solutions we're going to talk about. I'm sorry, you're back. Anybody have any questions so far about the different types of equations? Okay. The acids and bases. So the simplest definition of an acid-base is called the Arrhenius acid-base definition. You throw an acid in water, it forms H3O+. You throw a base in water, it forms OH-. Generally speaking, acids add positive charge, bases add negative charge. Okay, so in biological surfaces, which you'll learn are usually negatively charged. And so if you want to do something to a biological surface, like say you want to color your hair, what do? You put an alkaline, a base, into your hair, so sodium hydroxide lye, like that. What happens to your hair follicle? It blows up because you had negative charge to an already negative charged thing. It gets really big. And then you can put in dyes into the hair, or you can do chemistry with the dyes in the hair in there. And then you can rinse it off, and then you rinse off the base, and then your hair shrinks back down, and the dyes are stuck in your hair. So also, say you get stung by a jellyfish. You're swimming, you get stung by a jellyfish. What's the treatment for that? The first treatment is said to be done is you put an acid on it. You put vinegar is what they typically say. So why vinegar? Well, when you add vinegar, so the jellyfish are biological creatures, they have stinging cells. You add vinegar to it, it'll shrink the cells. And then it'll deactivate them. But now you still have the poison. The latest research from Manoa says the next treatment is to treat it with heat. If you want to do it, the best way to do it is to take a metal spoon and put it into hot water, as hot as you can handle, and then press that on the wound. And what that does, it denatures the protein. It changes the protein shapes. So that works for all protein-based poisons, as a matter of fact. So I can tell you, firsthand experience, it works for stingrays. So I got stung. I got stung by a stingray on my finger, actually. I'm one of the weird ones that did not get stung on his foot. So, and it really hurts. It's a tingling sensation. It goes down your limb, and then I put a hot metal spoon on it, and it neutralized the poison. Which is nice. So it works for bug bites too. What? Bee stings can also have formic acid in them, so it can do a little bit of both. It'll help. It'll help with the itching, but I mean the bee sting has got other things in it besides. It has and ant bites. Ant bites also have formic acid in them. So it's any venom. So bees do have venom as well, so it'll neutralize the venom, but the formic acid that's in the venom will not be neutralized. So by heat. What's that?
Baking soda. That's why.
Oh yeah,
Is that why you do that with these things?
I would assume so. I'm not. Yeah, no. That would get rid of the formic acid, especially if it's on the surface still, because then that would go in your bloodstream. Yeah. Okay, so and acids can be monoprotic. Most acids are monoprotic, meaning one proton. There's also polyprotic, so sulfuric acid, battery acid, that is polyprotic. In this case, it has two protons, two hydrogens. It's like, so 1 mole of sulfuric acid is actually 2 moles of acid because of the 2 H's. And we will talk about this much, much more in Chemistry 162, but here are some real common acids and bases. Hydrochloric acid, it's also the acid that's in our stomachs. Okay, so our stomach acid is hydrochloric acid. HBr, hydrobromic, hydroiodic. Of the 3, those are all strong acids. HI is the worst. It is very strong. In water, they're all about the same. But in gas phase, HI is the worst acid. Corrodes a lot of things. Nitric acid, We've already talked about nitric acid and how to make explosives, right? So TNT, trinitrotoluene, you take toluene and mix it with nitric acid, get in a 3-to-1 mixture, you get trinitrotoluene. Sulfuric acid, that's it's in battery acids. We make quite a bit of sulfuric acid. The vast majority of what we make with chemicals, well, actually, what we make the most of as far as our chemical industry is probably not a surprise, transportation fuel. That's the number 1 product. Can anyone guess what the number 2 product? Hint, we have an agriculture professor in here. What's the number 2 product that we make of? Yes, fertilizer. So fertilizer is our number 2 chemical that we make with our chemical industry. And we use quite a bit of sulfuric acid to make things like, so ammonium sulfate, very common fertilizer. So that's what we use the vast majority of all of our acids for is for chemical fertilizers. Perchloric acid, so it's another strong acid. That's used to make cheap fertilizer or cheap fireworks. If you know, maybe you've noticed. I guess we don't have too many fireworks. Do we have spark displays on Maui? I used to live on Oahu. We had them quite a bit, but they're shorter now because they changed the laws. You have to have nitrate explosives instead of perchlorates. So the firework displays, if you've noticed them, they're not as smoky and they're shorter because they're more expensive. So, ooh, and I'm looking at, acetic acid, that's what's in vinegar. Hydrofluoric acid, that stuff scares me. This stuff, it's a surface anesthetic. So if you get it on you, you can't feel it as it's burning you, and it's bone seeking. So it only get neutralized by calcium. So let's say you're working on something, you spill hydrofluoric acid on you. I've had this happen to 2 people I know. They hear this sound and they look down and see white foam coming from their fingers or hands. That's the hydrofluoric acid eating their bones, and they can't feel it. So, and the treatment for that, I mean, water ruins it off, but unless you neutralize it with a calcium something, it will continue to eat your bones. And it can kill you. A small amount can kill you because then you can get a bone chip go in your bloodstream that can cause a heart attack or stroke. So you have to use calcium glutamate. It's a cream that you rub on. And I've worked with fluorine gas, and I had to be trained in how to use that stuff. And also what's scary about hydrofluoric acid is it dissolves glass. So it's one of the few things, you can't store it in glass jars, it will dissolve glass, it has to be stored in plastic. And if you've ever seen frosty glass before, like someone you see frosty decorative glass, it's from hydrofluoric acid. So you take glass and you spray it with hydrofluoric acid and you get that frosty look. So bases, sodium hydroxide, that's also known as lye. L-Y-E, lye. It's also how we make soap. So if you wonder how soap is made, we take lye and you mix it with some sort of fat, plant or animal, and then so all fats here on Earth, for all living creatures, are typically stored as triglycerides, which means you have a 3-carbon glycerin molecule, and then you have 3 fatty acids attached to it. So all plants, all animals do that. And so it doesn't matter if it's an olive plant or it's a human or a cow, we all have a very similar fat structure. And that's how you make soap. We don't use too many of the other ones as much. Sodium hydroxides of the list, that's we use quite a bit of. Although it's listed as common, maybe common in a chemistry class. But, actually ammonia. Ammonia we do a lot of. And we talked about that in a previous class for fertilizer. Okay, so, but don't spend too much time looking at this. I know the book goes through quite a bit. We're just doing real simple things at this point in time. We're going to talk about acids and bases much more in depth in Chem 162. But what you do have to care about is how to write the equations. So the molecular and net ionic equations, for instance here, hydroiodic acid and barium hydroxide. So if you look here, we have an acid, so HI acid with barium hydroxide base forms water and a salt. So there are 2 definitions for salt in chemistry class. So the first definition is a metal plus a non-metal. That is, and the non-metal is not a hydroxide or an oxide. So that is one definition of a salt. The next definition of salt is it's the result of an acid-base neutralization reaction. So what do I mean by that? So we have chemical sensors on our tongues. So we can sense sweet, sour, bitter, salty, and savory, umami. So we have those 5 sensors. And acids, if you give acids to humans, you taste it, it tastes sour. Okay? If you give a base to a human and the human tastes it, it tastes bitter. And we are pre-programmed to not like sour or bitter. And so what do I mean by what's a bitter flavor? If you've ever drank like cheap NyQuil, like if you go to Walmart and buy generic NyQuil or generic Robitussin, and you drink that stuff, you have that, that is your bitter flavor. And the reason why humans don't like it is that most things that are bitter are poisonous. So we don't like bitter things. And so, for instance, you can form sodium chloride salt, which tastes really good, by taking hydrochloric acid, which tastes very sour. It's in our stomachs. We've tasted the stuff coming from our stomach before. It's really sour. We don't like it. I've never tasted sodium hydroxide, but I'm sure it tastes really, really bad. Don't taste it. But you have these two things that you mix together and you form sodium chloride salt. Does salt taste sour? Does salt taste bitter? No, it tastes salty, right? So that's something new. So we've proven then there's a chemical change. Sodium chloride is neither an acid nor a base, it's a salt. So a salt does not have the properties of an acid or a base. So, okay. All right, so when we write these equations, so HI, so first thing I do is balance the equation. And one of the ways I can shortcut this, I know that there's 2 hydroxides, so you're going to need 2 of those hydrogen ions to get those 2 hydroxides, and then we're going to form 2 waters. And then we look at then looking at the balancing, we have 2 iodines and 1 barium, and then same thing as on the right. So there are some shortcuts for balancing equations, because if you look at the grouping of the ions, you can look at them all as the groups of the ions as well, and not just the elements themselves. Because can you imagine if you try to balance the elements here? Because now we have hydrogen here and we have hydrogen there, so it'll make it much more difficult to balance that. So looking at that. The other thing with, if you know it's an acid-base reaction, acid-base makes water and salt. So, and that's what next line is what I just done. To change this to the complete ionic equation, we're going to have 2H plus 2I minus, and I'm implying these are all both aqueous, plus barium plus 2OH minus, yielding 2 waters. I'll go ahead and put that, oh, that's not solid, it's a liquid. This is liquid water plus barium, iodide, and all aqueous. But what else is happening? You're also, okay. Actually, I'll do the complete ion, sorry. I should keep this complete ionic. Plus barium plus 2I minus. And do we have spectator ions? Yes, we do. We have iodines here. We have barium there. And so when you look at any acid-base reaction, at least in water, the net ionic equation is, well, there's 2 of these. You can simplify it to just, we're making water. So that's the net ionic equation for acid-base. H plus OH minus makes H2O. And you might also notice that I before mentioned that we have H3O plus versus H plus. So the better way to do it is to use H3O plus. So H plus here, H plus is a proton, and by By computer simulations, it suggests that there's H3O plus. There's not really any free H plus in solution. So, but that's a computer simulation. That's not real data. Because H plus is just a proton, and we typically look at things by using spectroscopy, by looking at the electrons, H plus has no electrons. So it's really hard to probe it and figure out if it's right or not. So based off of what we can tell, and with computer simulations, we think it's H3O plus, but this is one of those we're not entirely sure. So, and there's not really any way that we can be sure either. So, but an H3O plus, it's just an extra hydrogen on water, and the whole thing, 3 protons, 1 oxygen with a positive charge. Okay, questions so far? All right, so you do have to know how to do this, titrations. So, and titrations is really an old thing, and part of me wonders about teaching some of this stuff. I mean, and I will teach it, of course, but we're getting increasingly to the point in time that most titrations are done by robots. Okay, so we're looking at putting a water quality lab here in Maui College, and we're looking at buying an instrument that can do 80 samples in a couple hours, and it's a robot. It just one arm goes in, grabs some stuff, comes out, spits it out, and we have that's when you get your blood work done at the hospital. They take your blood and they put it in a machine, and the robot does a titration. And it tells you, like, oh, this person has the wrong potassium levels. That's the reason why the person's having the heart murmur. Or, oh, the blood levels are fine. You know, so we just have a machine, a robot that does this. Of course, in chemistry lab, we have burettes. We measure it out. We put indicators. We look at the stuff. We swirl it around. That's what we'll do in class. But the majority of titrations, like I said, are done by robots. Very few are done by humans. Although I did mention I worked at Ecolab, they did titrations there. So there was one place that I saw people actually doing titrations. So, but those are becoming few and far between because as labor gets more expensive, do we hire 3 lab techs or do I get one machine that costs $80,000? So, answer is probably pretty obvious. So okay. So, and what is a titration? Simply put, it's a way to figure out how much stuff is in something, whatever it is I'm looking for. And I mentioned using an indicator. You can use an indicator or a pH probe. So a pH probe, when it reaches pH 7, then I know it's neutral. An indicator, you can put an indicator. So we're using, sodium hydroxide. You could use something called phenolphthalein. It turns pink. So I have the solution, and when the solution turns pink, I know it's done. So that's what an indicator does, and we use it by sight. So 10 milliliter sample of hydrochloric acid solution of unknown concentration requires 12.54 milliliters of 0.1 molar sodium hydroxide to reach the equivalence point. What is the unknown concentration of the hydrochloric acid? So titration, and in doing this, the moles of acid equals the moles of base. Well, I guess I have it backwards. The moles of base equals the moles of acid. So when we do this reaction and we have sodium hydroxide and hydrochloric acid. So, and one thing to note about this, it's a 1-to-1 because there's 1 proton and there's 1 hydroxide. So if we had strontium hydroxide and hydrochloric acid, we would need 2 moles of hydrochloric acid to 1 mole of strontium hydroxide because of this 2. Okay? Is that making sense? I'm getting some worried looks on your faces. Okay. And the other thing to note, and I have a problem for you next, instead of HCl, say we had H2SO4, that 2 there, the hydrogen there, that means, and if we had sodium hydroxide and sulfuric acid, we would need 2 moles of sodium hydroxide to 1 mole of sulfuric because of the ratio, that H ratio. Is that making sense? Okay, well, I'm getting some worried looks on your faces. Are you not following that? Okay, well, I'll check on you as we do the templates. Okay, so how do we do this? We can do this via the dimensional analysis. It's the easiest way to do this. We can look at sodium hydroxide, so 12.54 milliliters. And this is sodium, I should write it, it's NaOH. And liter to 1,000 milliliters. And then we have 0.1 moles sodium hydroxide to 2-liter solution. And then we have a mole of HCl per mole NaOH. And the last step is 0.01 liters, so 10 milliliters. So 10 milliliters equals 0.01 liters, right here. All right, so we're doing the dimensional analysis. 12.54 milliliters of sodium hydroxide, that's given. And we're having a concentration in molarity, M. Capital M means moles per liter. So we convert milliliters to liters. So right here now we have moles of sodium hydroxide. And there's a 1-to-1 ratio of hydrochloric acid to sodium hydroxide. So when we get here, we now have moles of hydrochloric acid divided by, so and then molarity is moles per liter, divide by the volume there to get that. You guys look happier now. You guys are following? Okay. So by doing dimensional analysis, and then you can put in your handy dandy calculator. Once I find my calculator. And the solution is 0.1254 molar HCl. Actually, no, we only have 3 sig figs. So we only know it to 0.125 molar HCl. Doesn't want to stick around. I'll put it over there. Okay. So a recap with this one. We're titrating hydrochloric acid, and we have a known concentration of sodium hydroxide, and this unknown concentration of 10 milliliters. We titrated with a known concentration. It takes 12.54 milliliters of this known concentration. So by using dimensional analysis, we can figure out then that we have, by using the logic like I talked about here, that our volume of known concentration will give us the moles of sodium hydroxide, 1-to-1 molar ratio between sodium hydroxide and hydrochloric acid. Then now we have the moles, we divide by the volume to get the concentration. So, questions with this? Okay. All right, and how many milliliters of a 1 molar sodium hydroxide solution are needed to neutralize 10 milliliters of a 1 molar sulfuric acid solution? And this is a tricky. This is intendedly tricky. This is easy and tricky at the same time. How many think we need 5 milliliters? How about 10? 20? 40? Okay, so we got some votes for, it's not A or D, it's going to be B or C. So write out the equation, NaOH plus H2SO4 yields H2O plus sodium sulfate. So what we balance it like so. So what is the molar ratio between sodium hydroxide and sulfuric acid? It's 2 to 1. So do we need the same amount or do we need double? You need double. The answer is C. Is that making sense? Okay. How are we doing so far? Questions about anything? All right. Next category of reactions, gas evolution reactions. And so you can, for instance, this is actually what they use in gas chambers. So you can execute people by gas chambers. And the way this is done is you mix hydrochloric acid with sodium cyanide salt. And what happens is sodium chloride is formed and then hydrogen cyanide gas. And in the olden days, like I said, the gas was denoted as an arrow pointing upwards. And I remember, so I've smelled hydrogen cyanide before. I can tell you it smells amazing. It smells like roasted almonds. It's really, really a nice smell. And I know this because I was in chem lab, and I remember I had the curse of the bad lab partner, and so I knowing that that hydrogen cyanide smells like almonds, and I'm in organic chemistry lab, you probably shouldn't smell almonds in organic chemistry lab. I was like, oh wow, roasted almonds. Like, what'd you do? And my lab partner said, oh, I mixed these two things together. It was acetic acid and sodium cyanide. And I was like, uh-oh. So held my breath and went to the window. And then I was worried. I told the teacher, I'm like, we just released some cyanide? And he's like, you're fine. And later on, the nice thing about cyanide poisoning, if you can get up and walk away, you are probably fine. So it takes quite a bit, actually, to kill someone with cyanide poisoning. Now that being said, that you know that sodium cyanide, that cyanide gas smells like almonds. So there's two things about it. First of all, if you smell it, it smells really strongly and then it disappears. That's one of the key signs that it's cyanide gas, because we as humans, we get used to smells. Have you ever noticed that? Like if you're in a room for a while and like, man, that smells really bad. Like, I don't smell it anymore. We get used to things. We don't get used to the variation of things. So, and if you're somewhere, so say you're walking around and you're in like a tank farm, something that has these big metal tanks everywhere, and you start smelling cyanide, you start smelling roasted almonds, you don't smell it anymore. That's when you turn around, you run, okay, because you're being exposed to cyanide. Say that you're at a farmer's market and someone's roasting almonds, and you smell roasted almonds, and you keep on smelling roasted almonds, you run out there saying, it's cyanide, run away. You are, in fact, smelling cyanide. So, but it's at a safe level. I mean, we can smell it pretty well. But almonds get their flavor from cyanide. So when you're tasting almonds, you're tasting cyanide. So maybe if you are of legal drinking age, you have consumed amaretto before. It tastes different than almonds because, among other things, the cyanide has been removed. To me, it has more of a cherry flavor. So than an almond flavor. Almond flavor it's like I said, cyanide. You're tasting cyanide. So, but just think of that. But like I said, doesn't mean if you smell almonds, it could be. I mean, you're smelling cyanide, but it's if you're at like a farmer's market or like a Christmas market, like it's probably fine. But if you're somewhere that it shouldn't smell like almonds, then it's dangerous, like ChemLab. Okay, so here are some common gas evolution reactions. So sulfides. So if you mix acids and sulfides, what's formed is H2S, hydrogen sulfide. And hydrogen sulfides, they smell really badly. It smells like rotten eggs. So we're about to learn about oxidation states. We as humans, we can smell sulfur in the -2 states. We can smell that down in parts per trillion. So we are really good at smelling sulfur. And so things like natural gas, they put, in natural gas, they put CH3SH, so methylthiol. They put this stuff in natural gas. Actually, like straight natural gas, it doesn't smell. Okay, but we put this stuff, the methylthiol, into it because we can smell it down the parts per trillion. And so it takes a little bit of it, but then, and the other thing is that humans don't like the smell of it. So I mentioned toluene before. We like the smell of toluene. It smells sweet. They put toluene in, like, you ever had like models before, had model cement? Like, that stuff smells good, right? You're like, ooh, let me smell some of that stuff, right? You put something that's really stinky that we can smell in a really small amount into natural gas. You're like, oh, someone left the gas on. Turn it off, turn it off, turn it off. Right, so you can smell it that way. So, okay, so hydrogen sulfide smells like rotten eggs, and like I said, you can smell it in a really small amount. I've never smelled it in a high concentration. I've read that in a high concentration, hydrogen sulfide doesn't smell, but I guess it just overloads our senses. But we're also looking at hydrogen sulfide to be used as for hibernation. Specifically space travel. So how do we get people to go to Mars? Well, we can hibernate them so they don't have to endure the 1.5-year journey all the way there. So, but the jury's still out on that one. It seems to work well on kids, but not necessarily adults. So now another one, carbonates. So carbonates, and bicarbonates. So the good old vinegar and baking soda volcano, mixing acid into bicarbonate or carbonate forms carbon dioxide. So the fizz from your volcano there was carbon dioxide. Sulfites and bisulfites. So in the word bi in chemistry class, so you see bicarbonate and bisulfite. Bisulfate, bi just means extra hydrogen. So carbonate is CO3, bicarbonate is HCO3. And ammonia, you can form, ammonia can be formed from ammonium compounds, so NH4. So ammonium chloride, NH4Cl, plus a base can form water and ammonia gas. And ammonia is interesting because it can knock you out and it can also revive you. So maybe you've heard of smelling salts before. Smelling salts are ammonium carbonate, and that's so if someone gets knocked out, he or she might be revived by inserting smelling salts into the person. And it's if you've ever smelled ammonia in a strong amount, it's a full body jerk. It's pretty strong. Okay, I'm not going to go through any examples of this because we've already talked about precipitation reactions quite a bit. We've already done acid-base and the gas evolution. I think you have enough. It's the same category. Oh, is it? Jeez. I thought I quit Skype. I tried to quit you, Skype. Okay. But does anybody have any questions about acid-base or about gas evolution? Okay. Last topic we're going to get into. I don't think we're going to finish it today, and this is the last topic, mind you. So this is I know we changed topics so much. This is the last topic of the chapter. So Oxidation and reduction. So oxidation, there are three definitions. Oxidation means addition of oxygen. So if you have iron metal and you oxidize the iron metal to iron oxide, you've added oxygen to iron to form iron oxide rust. That's oxidized. You take an apple, you slice it up, it starts turning brown. What's happening? It's oxidizing. What's happening? Oxygen is combining with the little bits of iron and other things in the apple to change the color. It's reacting as oxidizing. Oxidation can also mean removal of hydrogen. So this is more important when you get to organic chemistry. So you can oxidize ethylene to form ethine. So ethylene is C2H4, ethine is C2H2. So removing hydrogen from ethylene oxidizes the ethylene to ethine. The most general term for oxidation is removal of electrons. So this is the most general. So meaning, so I mentioned iron oxide. So iron reacts with oxygen. Oxygen takes the electrons away from iron, and now we have iron oxide. Iron oxide is usually +3. So iron starts with all of its electrons. Oxygen comes in, rips 3 electrons off. Oxygen gets 2 electrons. So now we have iron with 3 fewer electrons and oxygen with 2 extra electrons. So the most general term for oxidation, and works for all cases, oxidation means ripping off electrons, removing electrons. So now let's use logic. If oxygen is added to something, something has to lose oxygen. And if something is removing hydrogen, something gets hydrogen. And if something is losing electrons, something is gaining electrons. Of course, the most general term works here for reduction. So if in oxidation, losing electron works in every single case. And that means if electrons are removed, where those electrons go, they go to somewhere else. That species that gets the electrons are reduced. So, so using that logic, I mentioned oxygen, and so iron oxide. So iron oxide, iron is gaining oxygen to be oxidized. What loses oxygen? Oxygen does. O2 gas. The gas is being destroyed. So the oxygen itself loses oxygen. And it's kind of weird, right? Same thing with reduction. So I mentioned you can go ethylene to ethine. Oxidation, you can go the other way too. You can go ethine. Also, I should probably say acetylene. So acetylene, ethine. You can add hydrogen to that, and you can do it over a catalyst like platinum, and you can form ethylene, C2H4. You can also form ethane, C2H6. So you can add hydrogens, and then that's a reduction. Why is adding hydrogens considered reduction? Because hydrogen is said to be very electron rich. So adding hydrogen to a compound adds electron density to the electron cloud. So we'll talk about the electron clouds, of course, later. And reduction is, in general, gaining electrons. So these reactions happen hand in hand. So meaning whenever something is oxidized, something is reduced. And whenever something is reduced, something is oxidized. It's just transfer of electrons. So since they always happen together, we call oxidation reduction reactions, frequently call them redox. So why redox? Because it's just the first 2 letters of oxidation and the first 3 letters of reduction. And redox sounds smoother than ox-red. So because you say ox-red, you think of like an ox painted red, right? So redox sounds like, okay, that sounds more intelligent. So, okay. Now, the next thing we're going to do is learn how to assign oxidation states. So, and these rules are hierarchical. So let me talk about an oxidation state first. An oxidation state is a way of keeping track of where electrons are. So later on, when we talk about Lewis structures, you're going to learn about something called formal charge. So in formal charge and bonding atoms, each atom gets half of the bonding electrons. Oxidation states, one element gets all the electron. So, and also we'll learn later on, electrons are not dots. They're actually this kind of fuzzy cloud. There could be in many different places at once. You can actually have electrons shared across many different things. So electrons are not like, they're not classical, meaning they're not like my cell phone, where my cell phone is here in my hand. It's not in my hand and in the toilet and the bathroom at the same time. It's only in one or the other. Quantum mechanics, which we'll learn, they actually can be in both places. So, but to simplify things and to keep track of electrons, we use oxidation states to say where electrons are. And it's just one way of keeping track, and it also lets you know how much electrons are around the specific elements. Okay, now these rules are hierarchical, which means that rule 1 is more important than rule 2 and so on. So rule 1, oxidation state of a free element is 0. So any free element, the oxidation state is 0. Next one is the oxidation state of a monatomic ion is equal to its charge. So monatomic, 1 atom. So mono means 1 atom. Rule number 3. So the sum of oxidation states for all atoms in a neutral molecule or formula unit is 0. Or an ion is equal to the charge of that ion. So remember, keeping track of electrons here. In compounds, alkali metals, group 1A, always +1. Alkaline earths, always +2. And then in other compounds, we have this table here, and this table is also hierarchical as well, that fluorine tends to be -1, hydrogen tends to be +1, oxygen tends to be -2. Group 7A halogens tend to be -1. Group 6A oxygen family tend to be -2. Group 5A nitrogen family tends to be -3. So let's use these to look at oxidation states. So first one here, Cl2 chlorine. So Cl2 chlorine, this is a free element. We have only chlorine. Because of that, and frequently oxidation states are put in the upper right corner. Oxidation state of chlorine is 0. So next one, so that's rule number 1. Free element is 0. Everyone okay with that? Next one, sodium. Oxidation state is the monatomic ion. Rule number 2 is a monatomic ion is equal to its charge. Sodium's is +1. Or plus. Plus usually means +1. Okay, so next one here, potassium fluoride. This is a compound. And rule number 3 says that the oxidation state of potassium plus the oxidation state of fluorine equals 0. And if we then go down to rule number 4, alkali metals always are +1. So potassium is going to be +1. Let's get 7. +1. So +1 plus fluorine equals 0. That means fluorine is -1. So fluorine there is -1. You guys good with that? CO2. So oxidation state for carbon plus, and I'll change color for oxygen. Actually, the sum is equal to 0. Actually, I should get rid of So carbon plus 2 times oxidation state of oxygen is 0. And if you look at the chart, so rule number 4, not alkali, not alkaline earth. Number 5 of the chart. Then we go down, then we go to oxygen. Oxygen tends to be -2. So carbon plus 2 times -2 equals 0. So I'm just going to put -2. Then carbon plus a -4 equals 0. Carbon equals +4. So like that. Are you seeing the logic there? All right, next one, sulfate. So just like for carbon dioxide, we have sulfur plus 4 times oxygen equals -2. And So what's different about this one? This one is charged. This is a charged ion, so that's where we get the -2. So oxygen tends to be -2. Oh, there's my shut up alarm. My shut up alarm says class is over. So, anybody have any questions? Okay, well, you're free to go. Oh.